Inside the core of a modern turbofan engine, conditions are nothing short of apocalyptic. Temperatures soar to over 1,500 degrees Celsius or 2,700 degrees Fahrenheit, a heat so intense it exceeds the melting point of the metal components themselves. This is the ultimate engineering paradox. How do you build a machine that doesn't melt while it's running? At 30,000 feet, these engines are the most complex machines ever mass-produced, consisting of over 40,000 individual parts working in absolute harmony. The pressure inside the compressor is 40 times that of the atmosphere outside, and the centrifugal force on a single turbine blade is equivalent to the weight of a loaded semi-truck. Every second, the engine breathes in enough air to empty a squash court, compressing it, igniting it, and harnessing the explosion to propel hundreds of tons through the sky. Today, we go beyond the casing to explore the extreme metallurgy and invisible cooling physics that make the modern jet engine a miracle of human ingenuity. From the raw superalloys to the precision-drilled cooling holes thinner than a human hair, this is how we build the heart of the modern airliner.
It all begins with chemistry, because ordinary steel, or even titanium, would soften and fail within seconds inside the high-pressure turbine. Engineers turn to nickel-based superalloys, materials engineered at the atomic level to resist creep, which is the tendency of a solid material to move slowly or deform under mechanical stress. These alloys are a precise cocktail of nickel, cobalt, and rare earth elements like rhenium and ruthenium. Rhenium is one of the rarest elements on Earth, added to prevent the metal from losing its shape at extreme temperatures. These raw materials are melted in a vacuum induction furnace to prevent any contamination from oxygen. If even a tiny bubble of gas or a microscopic speck of dust enters the mix, it could create a fracture point, leading to a catastrophic engine failure mid-flight. The molten metal is then carefully monitored as it readies for its transformation into a single, unbreakable crystal. This isn't just metal, it's a high-performance ceramic-metallic hybrid designed to survive the impossible, and it is the only reason we can fly at Mach 0.85 across the Atlantic every single day with total reliability.
The turbine blades are the most stressed components in the engine, and their strength comes from a process called single crystal casting. In a normal piece of metal, there are millions of microscopic boundaries between individual crystals, called grain boundaries. Under high heat, these boundaries act like cracks, allowing the metal to stretch and eventually snap. To solve this, engineers grow the entire blade as one single continuous crystal. The molten superalloy is poured into a ceramic mold inside a vacuum furnace. At the bottom of the mold is a grain selector, a tiny corkscrew-shaped path. As the metal cools from the bottom up, only one single crystal is able to navigate the spiral and grow into the rest of the mold. This process takes hours of precise temperature control. If the cooling rate varies by even a fraction of a degree, multiple crystals will form and the blade will be scrapped. The result is a part with no internal boundaries, a single perfect lattice of atoms that can withstand the brutal centrifugal force of spinning at 12,000 revolutions per minute, while resisting the softening effects of the inferno. It is a masterclass in molecular engineering. Even a single crystal superalloy has its limits. To survive temperatures 300 degrees hotter than its own melting point, the blade needs a shield. This is where thermal barrier coatings, or TBCs, come into play. Using a process called electron beam physical vapor deposition, or a high-velocity plasma spray, a layer of specialized ceramic called yttria-stabilized zirconia is applied to the blade. This ceramic layer is only about 200 micrometers thick, roughly the thickness of 2 sheets of paper, but it acts as a powerful insulator. It creates a temperature drop of up to 300 degrees Celsius between the hot gas and the metal surface. This coating has a structure like microscopic columns, allowing it to expand and contract as the blade heats up and cools down without flaking off. Without this invisible ceramic armor, the metal would lose its structural integrity almost instantly, turning the engine into a molten mess. It is the same technology used on the heat shields of spacecraft re-entering the atmosphere, repurposed to keep you cruising at 35,000 feet reliably and safely for thousands of hours.
Beyond the coating, there is a second, even more complex line of defense: film cooling. Each turbine blade is hollow, featuring an intricate, labyrinthine path of internal cooling channels. High-pressure air is bled from the compressor at the front of the engine and piped into the center of these blades. This air is cooler than the combustion gases, though still several hundred degrees itself. It flows through the internal maze, soaking up heat from the metal, and then exits through thousands of microscopic holes laser-drilled into the surface of the blade. These holes are drilled at precise angles, designed to create a thin, protective film of cool air that clings to the surface of the blade. effectively wrapping it in a cold blanket. This film prevents the 1500-degree combustion gases from ever actually touching the metal. These holes are so small they can be clogged by a single grain of sand, which is why engine filters and air purity are so critical. This internal architecture is often made using sacrificial ceramic cores that are dissolved away after the metal is cast, leaving behind a hollow cooling heart that defies the laws of thermodynamics.
While the turbine handles the heat, the front of the engine, the fan, handles the mass. The fan blades on a large jet engine like the GE90 are over 4 feet long and made of lightweight titanium or advanced carbon fiber composites. These blades are the engine's primary source of thrust, pushing massive amounts of air around the core rather than through it. This is known as bypass air. At takeoff, each blade generates the same amount of centrifugal force as the weight of 2 Boeing 747s, pulling outward with incredible intensity. To save weight, many of these blades are hollow, consisting of 2 titanium skins with a titanium honeycomb or web structure diffusion bonded in the middle. The leading edge is often reinforced with solid titanium to protect against bird strikes, which can impact the engine with the force of a small cannonball. Every blade is balanced to within a fraction of a gram. Even a tiny imbalance at high speeds would create vibrations that could shake the entire aircraft apart. This is the front line of propulsion, where massive scale meets surgical precision to create the quiet, efficient power of modern flight. All of these spinning components must be connected to a central spine, the main shaft. This is a massive, high-strength steel beam that runs the entire length of the engine, connecting the turbine at the back to the fan at the front. It must be perfectly straight and incredibly rigid, yet capable of twisting slightly under the immense torque of the engine. The shaft is supported by high-precision bearings that are constantly bathed in a mist of synthetic oil, cooling them and reducing friction to nearly zero. These bearings must handle both the radial loads of the spinning parts and the axial loads of the thrust pushing the engine forward. Surrounding the shaft are the compressor discs, dozens of circular plates that hold the smaller compressor blades. These are shrunk fit onto the shaft, a process where the discs are heated to expand, slid onto the cold shaft, and then allowed to cool, creating a bond so tight it's essentially one solid piece of metal. This central assembly is the backbone of the machine, the bridge between the energy of combustion and the mechanical force of propulsion, and it must operate without failure for tens of thousands of flight cycles.
A modern jet engine doesn't just run, it thinks. Controlling this mechanical beast is the FADEC, the Full Authority Digital Engine Control. This is a redundant, high-speed computer mounted directly on the engine casing, and it acts as the engine's brain. It monitors thousands of data points every second, including air temperature, pressure, fuel flow, and vibration levels. When a pilot moves the thrust lever, they aren't directly controlling the fuel, they are sending a request to the FADEC. The computer then calculates the exact amount of fuel needed, the precise angle of the variable stator vanes, and the optimal cooling flow to provide the requested thrust while protecting the engine from damage. It can detect a flameout or a compressor stall before it happens and take corrective action in milliseconds. The FADEC also records every second of flight data, allowing maintenance crews to see deep into the engine's health and predict when a part might need replacing. It is the digital master of an analog inferno, ensuring that no matter how hard the pilot pushes, the engine remains within its safe operating limits, every single time. Before a new engine design can ever carry its first passenger, it must survive a gauntlet of torture tests that would destroy any other machine. In specialized test cells, the engine is pushed to its absolute breaking point. Engineers fire dead birds into the spinning fan at hundreds of miles per hour to ensure the casing can contain any broken blades. They blast the engine with tons of water and slush per minute, simulating the most intense tropical storms or icing conditions to make sure it doesn't flame out. Perhaps most dramatic is the blade-off test, where a small explosive charge is detonated on one of the fan blades while the engine is at full power. The engine must be able to shut down safely without the shrapnel piercing the outer casing, essentially acting as its own armor. These tests are brutal, expensive, and absolutely necessary. They prove that even in the most extreme, unlikely scenarios, the engineering will hold, and the passengers will remain safe. Only after passing these trials of fire, ice, and impact is the engine certified for flight, a testament to the thousands of hours of simulation and design that preceded it. The modern jet engine is more than just a piece of hardware. It is the culmination of a century of progress in physics, chemistry, and manufacturing. It represents our ability to master the most hostile environments imaginable and turn them into a reliable tool for global connection. From the single crystal turbine blades grown in a vacuum, to the ceramic coatings that defy melting, to the digital brains that manage the flame, every component is a peak achievement of human skill. Today's engines are 40% more fuel efficient and 75% quieter than those of the 1960s, allowing us to travel further, faster, and more sustainably than ever before. As you sit in your seat and hear that low hum of the engines, remember the 1,500-degree fire raging just a few feet away, and the incredible engineering that keeps it perfectly contained, push after push, flight after flight. This is the heart of flight, a masterpiece of precision, and the ultimate engineering chronicle of our time, the jet engine, built to endure the heat and conquer the sky.
I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.